Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on March 5th, 2026, just yesterday. It introduces a hybrid neuro-symbolic approach that successfully solves a persistent open problem in theoretical physics, calculating the exact power spectrum of gravitational radiation emitted by cosmic strings. The paper is titled, Solving an Open Problem in Theoretical Physics Using AI-Assisted Discovery. And as we will see later, the mathematical derivations they achieved are really impressive, with significant implications for the future of artificial intelligence-driven scientific discovery. So, Figure 1 shows the verification of the analytical solution found by the artificial intelligence system, specifically the Gegenbauer method, or Method 6. This method works by expanding the mathematical function to naturally absorb its problematic singularities. The solid curves represent the newly derived closed-form expression for the core integral. These are plotted here for several different values of the parameter n. The open circles along those curves denote reference values obtained through direct numerical integration. Because the solid lines and open circles align perfectly across all angles, this agreement strongly validates the derivation. It confirms the system discovered an exact, stable solution. Alright, Figure 2 compares the 6 methods identified by the artificial intelligence system. The top panel plots their absolute error across different angles, for an n value of 20. Notice how Method 2, the Gaussian approach, diverges wildly, hitting errors near 10 to the 15th due to numerical instability. Meanwhile, the stable spectral methods stay right at the bottom with minimal error. Then, the bottom panel compares computational speed. The spectral methods evaluate orders of magnitude faster, though you can spot a brief time spike for Method 5 around 1.05 radians, caused by a temporary mathematical conditioning issue. Okay. Figure 3 illustrates how the new asymptotic formula converges toward the exact solution as the harmonic value n increases. The 3 panels show results for n equals 10, 100, and 1000. In the left panel, for n equals 10, the dashed asymptotic line deviates noticeably from the solid exact curve at smaller angles. However, the middle panel shows that for n equals 100, the approximation improves dramatically. Finally, the right panel demonstrates that at n equals 1000, the asymptotic formula perfectly overlays the exact calculation, confirming the prediction for large n behavior. Well, Table 1 summarizes the 6 methods discovered by the artificial intelligence system, comparing their core techniques and numerical stability. Methods 1, 2, and 3 rely on monomial expansion, which proves highly unstable due to severe cancellation errors. They also scale poorly, showing a computational complexity of order n squared, meaning calculation time grows quadratically as the problem size increases. In contrast, the remaining methods operate with highly efficient linear complexity. Method 6, the Gegenbauer technique, stands out as the optimal choice, because it provides a completely stable, exact analytic solution. Alright, wrapping up, 2 key takeaways stand out. First, combining large language models with rigorous search algorithms can successfully solve complex, open mathematical problems. Second, finding this exact formula for cosmic string radiation represents a major leap for artificial intelligence-accelerated scientific discovery. That is it for this episode of the Artificial Intelligence Research Roundup. I am Alex. Thanks for listening.